In this video, we are going to look at another useful technique for proving a language that is not regular. In other words, we're going to find another necessary condition for a language to be regular. Okay, so last time we looked at the pumping lemma for regular languages. So pumping lemma is a necessary condition. But then there is another form of this condition, of a necessary condition, and that is called FoolingSets. Okay, so let's look at what a fooling set is. So let L be any language. Okay, so here L is any language. Let me change the color here. Change it to blue. Okay, so that means L doesn't have to be regular. Okay, it is just any language. And then a fooling set, let's call it F sub L of L, is set of strings. Okay, so it is a set of strings with the following property. Okay, so any pair of distinct strings X and Y in F sub L can be distinguished by some string Z, meaning either XZ is in L or YZ is in L, but not both. Okay, so in other words, so let L be a language and FL be a set of strings, let's call them S1, S2, which could be finite or could be infinite. Okay, and then for each pair, so for each pair, so this I is not equal to J, Xi and Xj are distinguishable. So if for any pair I and j, where I is not equal to j, x and xj can be distinguishable by z, meaning, so let me remove this, for any pair of I and j with I is not equal to j, there exists a string z such that xiz is in L or xjz is in L, but not both. Okay, so actually this is an exclusive OR. All right, and FL is called a fooling set. So this is an example. So we let L be, so we let this L be a set of strings with an even number of zeros and an odd number of ones. Then this set of strings, we have 4 strings. This F sub L is a fooling set. Okay, so here we have 6 pairs, right? 0, 1, and 101. With this, with that, I got 3, right? So this is 4. So this is, we have 4 elements. So the total number of pairs here is k. So it's 4 times 3 divided by 2. That's equal to 6. So for this, 0, 0, 0 distinguish 0, 1, and 1, 0, 1 because you put 0 here. So we got even number of zeros and odd number 1. So this is in L. You put 0 here. We have even number 1. So this is not in L. Likewise, if we put 0 here, this is in L. But this is, you put 0 here, we got odd number of zeros and odd number 1. So this is in L. And this is in L. This is not in L. Okay, so you put 0 here, you get odd number of zeros and even number 1. So this is not in L. You want even number of zeros and odd number of ones. Okay, so for this 2, okay, so this is a 101 with 0, 1, 0, right? So for this we can put 1. So this is in L. This is not in L because you only have odd number of zeros. But if you put 1 here, so you have even number of zeros in this case and odd number of ones. So this is in L. Sorry, I guess I moved down too quick. Let me start over again. We do this, okay? So we put 1, 0. This we got odd number ones and even number of zeros, and you put 1, 0. You got odd number of zeros, so this is not in L. For this, I put 1, so this is not in L because you have odd number of zeros. You put 1 here, then this is in L. And for the last pair, put 1, this is, so you have even number 1, this is not in L. You put 1 here, put 1 here, then this is in L. So this is a fooling set for, this is an example of a fooling set. All right, so now we're going to make a connection of fooling set to a regular language. And we have this theorem that let L be a regular language and M be a DFA that accepts L with K states. Okay, so the length of Q is K. Then any fooling set FL, F sub L of L consists of at most K strings. Okay, so the idea to prove it is that first we are going to extend a standard transition function delta to allow a transition on a string rather than on just a input. Okay, so we'll call that delta star. So delta star on any state P and on an input string AX, where A is a alphabet symbol and X is a string, it is equal to delta star QPA. So this goes to another state, let's say Q, and then on X. So the idea is that we are going to, for instance, originally you get only on symbols, you get that. But now I just want, so I want to condense this. So this is delta. Let's say this is P, right? So I want to condense this to 1 steps. So this is X on P. So let's call this Q. Okay, so I condense or compress all the intermediate steps into just 1 arc or 1 link, but I put the input here as a string X. So with this, then we have the following. For instance, if a string, So we can get a string X, then this is Y. So now this is, so X and Y are both strings. Okay, and also we can say if, so this is Q0X. So this is really means that on these two strings, they will end up at the same, let me remove this. They will end up at the same state, right? So this is same, oops, so this is X. This is X. Okay, so this one delta, so X is a string. And then on the different Y, it also goes to there. So it ends up at the same state. And then from this, okay, then you just put a Z, obviously. If XZ is accepting, so ends at accepting state, YZ will also end at the accepting state. So these are sigma. Okay, so that's what we have. So that means if delta star, okay, this is true, then XZ is in L if and only if YZ is in L. So we already showed this here. And this is the description in words of this diagram. So once we know this, then we know that F sub L cannot consist of more than K states, because if it does, let's say it contains K plus 1 states. Say this is K plus 1 states, right? Then since, so on this edge, you have K plus 1 states, and we only have K different states available. That means some of these, somewhere here, they will be the same. So then for these two, so that means, now once again, let me probably open up a new screen, okay, to explain this better. Okay, so we can say FL, let's say now it has L state, L strings, and L is greater than K. Okay, so that means so for each xi, we start from Q0, then it ends at a state. So this is a state. So because you have greater than K many states available, that means that there exists I j with xi not equal to xj, such that they will end at the same state. So if we do, so we can say this is the beginning. And then here we got xi And then the other one, xj. Okay. And we have all together. So let me put it this way. So start from the initial state. Okay, we got x1. This is a delta star. Not so these x I, these xi's are strings, and then xl. So some of these two will have to be the same. So let's say this xi and xj are the same, right? So we call them I and j. So if this is the case, then xi and xj cannot be, they are not distinguishable, because if one, so this is for any z, because this is for any z, if xiz is in L, then xjz is in L. Okay, so they will both hold or both not hold. So that's not distinguishable. Okay, so that is theorem, pretty straightforward. Okay, so now then we can see this lemma. Okay, so this is just indicates that, okay, if L is irregular, then any Fooling set of L has to be finite. So if you can come up with an infinite Fooling set for a given language L, then L cannot be regular. Okay, so using infinite Fooling set to show a language is not regular could be easier and will probably be easier than using the pumping lemma. So now here we can see some examples. For instance, the first example is the one we use when we talk about pumping lemma, that L is equal to 0 to the n, followed by 1 to the n. For any n greater than or equal to 0, we know it is not regular. So we can prove it using FoolingSets without using the pumping lemma. So in this particular case, I just need, so the FoolingSet is just 0 star. So the set of all strings made up of 0, including the empty set. So then we want to show that this FL is a Fooling set. Obviously, it is infinite. In order to show it's a Fooling set, so we just let any x and y, which is a string, which are strings of zeros, and with x is not equal to y. So that means that there are I and j such that x is equal to 0 to the I. That means I zeros, and y is a string of j zeros. And so then we just let z be 1 to the I. Then we know that xz is 0 to the I, followed by 1 to the I. It is in L. But then yz is 0 to the j, followed by 1 to the I. since j is not equal to I, so it is not in L. So we have an infinite Fooling set for L. Hence, L cannot be regular. The next example, you are given a even length palindromes. Okay, we can write it as WWR, and it is not regular. So, we just want to come up with or construct a infinite Fooling set. So that f sub L be 0 star 1. So a sequence of zeros followed by 1. Then it is infinite and a Fooling set. So infinite is obvious. By infinite it's obvious. So now let's look at why it is a Fooling set. In order to see this, we consider any strings, any pair of strings x and y in f sub L with x is not equal to y, so that means that there are I and j with I not equal to j, such that x is equal to 0 to the I followed by 1, and y is equal to 0j followed by 1. So we let z be 1 followed by 0 to the I, so we know xz is 0i1 followed by 1, 0i, so this is in L. But then yz is 0j1 and then 1i, which since j is not equal to j is not equal to L, is not in capital L. So as you can see here, it is easier than using the pumping lemma to show these two languages, to show that these two languages are not regular. So next, we're going to see another example. Okay, so L, which is 0 to the 2 to the n for any n greater than or equal to 0, is not regular. So again, we want to construct a infinite Fooling set. So in this particular case, the Fooling set is L itself. Okay, so first of all, we're going to show that for any m and n, okay, if m is not equal to n, then you add these two numbers together. So we're going to show that, so this fact for any m not equal to n, you add 2 to the n plus 2 to the n, it cannot be a power of 2. So in other words, if it's equal to a power of 2, then we'll get a contradiction. Okay, so for this, we assume that m is less than n. If n is less than m, then we just divide both sides by the smallest value of m and smaller value of m and n. Okay, so of course we know that because 2 to the n plus 2 to the n is equal to 2 to the L, L has to be greater than m, and L has to be greater than n. So if m is less than n, m is less than n, we divide both sides by 2 to the m. So this is equal to 1 plus 2 to the n minus m. It's equal to 2 to the L minus m. You move this to the right. So what we are getting is 2 to the L minus m minus 2 to the n minus m, which is equal to 1. But we know that this is an even number. This is also an even number. And the first one's greater than the second. So the difference of two even numbers cannot end up at 1. Okay, so this is a contradiction. So hence, if m and n are different, then there is no L such that this is true. Okay, so that's a preparation. So once we have this preparation, then the rest of it would be straightforward. So now we want to show that L itself, okay, is a Fooling set. It is infinite, obviously. So to show that it is a Fooling set, so we let any string in L, x and y, with x is not equal to y, then there are I and j such that x to the 0 to the 2 to the I and y is equal to 0 to the 2 to the j. Without loss of generality, we assume that I is less than j, then we just take z, b, to be 0 to the 2 to the I, so then xz is 0 to the 2 to the I, followed by 0 to the 2 to the I, so that is how many zeros you have? That's 2 times 2 to the I. So this is really just 2 to the I plus 1. So this is in L, but then yz is 0, 2 to the j, 0, 2 to the I. So this is 0, 2 to the 0, 2 to the I plus 2 to the j. We know that there is no L such that 2 to the I plus 2 to the j is equal to 0 to the 2 to the L. So this means not in L. Small l. Okay, so this is small l. So that means this language is not regular. So now we see one more example. This is 0 to the p. So language L is the set of 0 to the p. So you have this. So this is a string of zeros, but the number of zeros is exactly p. P is a prime number. And then it is not regular. Okay, so we just let f sub L be 0 star. So set of strings made of zeros. And it is infinite, and we are going to show that it is also a Fooling set. Okay, so to see this, again, we let any x and y in f sub L with x not equal to y. Then we know there are I and j such that x is equal to 0 to the I, and y is equal to 0 to the j without also generality, assume that I is less than j. So now we let p be a prime number with p greater than I and p greater than j. So now, so this is a trick. So we know that p plus 0 times j minus I, which is equal to p, and that p is a prime. And then p plus p times j minus I is equal to p times j minus I plus 1. So this is greater than or equal to 2. So it has a factor that's greater than or equal to 2. Hence, this p times this things that's greater than or equal to 2 is not a prime. So now you can see here, then we have p plus 0, which is a prime, and then p plus p, which is not a prime. So then we wonder whether P plus P minus 1 is a prime. Now, if it is a prime, it could either just be two cases. Either it's a prime or not prime. If it's a prime, then I'm going to stop here. If it's not prime, then I'm going to keep doing it and see whether this P minus 2 times J minus I plus P is a prime. If it is a prime, then I'm done. Otherwise, I will keep doing it until you go. The worst case is you go down to 0. So at that case, we know it's prime, then we stop. So at a certain point, it's a stop. It will stop because in the worst case, it go down to 0. So when that is a prime, I let that value to be k. Okay, whatever the p minus something is okay, and then the previous one is P plus K plus 1 times J minus I, that's not a prime. Okay, so then we're going to form a witness, okay, Z, distinguishing, which is equal to 0 to the P minus I plus K minus 1 times J minus I. Okay, so this guy could at most be 0. So it's because P is greater than I, so Z is a string of some zeros. So you put Z at the end, so we get so X is equal to 0 to the I. So XZ is 0 to the I plus P minus I plus K minus I, J minus I. So this I canceled, so that's equal to this. We know that this thing is a prime, so it is in L. And then if you do YZ, so this is equal to 0 to the Y, which is 0 to the J. Y is equal to 0 to the J. And then plus P minus I plus K minus 1 J minus I. So you got J minus I here, so that becomes 0 to the P plus K times J minus I. We know this is not a prime, so it is not in L. Okay, so that is the end of this video. As we can see here, that using FoolingSets, constructing infinite FoolingSets for a given language is an easier way to work with to show that this language is not regular.